So we've now seen how to pass arguments on the stack. Let's see how we can use the stack for both allocating local variables to a procedure and for saving registers that we have to restore to the right value for all the procedures involved. Let's start with the register saving conventions. Let's go back to that procedure U and procedure WHO that we've talked about before. Remember, U is the caller and WHO is the callee. Let's take a look at this code here, and we see that just here's the call to WHO, but just before that we put a value into EDX, and then we expect to be able to use it after the call to WHO. So in the function U, we would hope that the value of EDX would not be disrupted by what might happen in the call to WHO, so that the same value is still there when we return. So in WHO, however, which might have been written by a different programmer, EDX might get a new value, and that would destroy the one that we had before, because there is only one register EDX in our CPU. Different procedures might use it, but it's the same physical register. So we have to make sure that the contents of that register, which is overwritten by WHO, gets saved somewhere before that happens. So what we have is some register saving conventions that are split between caller save and callee save. In the caller save case, the caller procedure saves the values in the registers before calling the other procedure. Callee save is complementary. It says the callee will do the saving before using that register. So when do we use each? When does the caller save a register, and when does the callee save a register? So it turns out that what we're going to do is have three registers be caller save, EAX, EDX, and ECX, and three registers be callee save, sort of split the responsibilities, okay? And then of course we have two special registers that are the base pointer and the stack pointer. Those are handled a little bit differently, but also involve restoring them to their original values upon exit from a procedure. Okay. The last thing to remember is that EAX, the reason also it's caller saved is because, remember, the returning procedure puts its return value in EAX. And so if the caller wants to use what it had in EAX previous to the call, it better save it somewhere else. Okay. And where might it save it? Probably in memory somewhere. Okay. All right, now let's turn to local variables. All right, here we have two functions. We have a factorial function called sfact, which calls a helper procedure inside of it. The way this works is that we create a starting point for the factorial, in this case the number 1 here at the beginning of sfact. And what we're going to do is pass a pointer to that value, an address, along with the value of the factorial we want to reach, x, and pass that to a helper function, which is defined here on the left. Okay, the helper function is going to see if x is less than or equal to 1. If it is, it's just going to stop. And if it's not, it's going to perform the multiplication of x times that value, that address that was passed to it as an argument. So you'll notice that that address of val was passed to this helper function as a pointer, right? And then we dereference the pointer to go get that value and multiply it times x. So when we start here, let's say that x was equal to 3, right? We would start with shelper being called with the value 3 and the address of val, which is has a value of 1 stored at that address. So when we come here to the shelper procedure, what we'll find is that x is 3 and The value stored at the address of val is 1, so we'll do a multiply 1 times 3 and store that back into that address we were passed as an argument, again by using the dereference operator. Okay, so now val is going to be equal to 3. But now shelper calls itself recursively, this time with the value 2 and the address again of that same place, although this time we refer to it by its local name, accum, right? So this is also ACCUM, the same address that we passed in. So now when we do this call to shelper, x will be 2, and the value that we dereference with the pointer is that one that we just stored away earlier, 3. So now we'll do 3 times 2 and put a 6 at that place, at that address of value. All right? And you'll see that the next time, of course, shelper is called now with 1 and the address of our accumulating product. And this time, the procedure will just stop right away and return. Okay, so how does this actually get implemented in our stack? So let's start with that sfact procedure at the very beginning. And here's the code corresponding to sfact, or at least some of it. Here is the stack inside of sfact. You'll notice that it has a return address to where it was called from, and its argument, x, the value x that it was given to start with. Okay, the very first procedure does that setup stuff we always do at the beginning of a procedure, adjusting base pointers. So we're going to save our old base pointer by pushing it onto the stack, and of course ESP, the stack pointer, adjusted as well. Then we are going to adjust the value of EBP to be to this new start of this frame pointer, of this frame on the stack. And then you'll notice we're going to subtract 16 from ESP, creating this temporary space on the stack, essentially allocating 4 words, 16 bytes, on the stack for use by local variables. Now in this case it turns out we're not going to really use all of that space. We only needed 4 bytes, but for argument's sake let's allocate 16. The next thing that we do is go get the value of x by accessing the location where that argument was stored. Remember 8 plus the base pointer. Okay, we get the value of x, and then we set the value of val. And how do we set the value of val? Val is a local variable declared inside the procedure, and you notice that we've made a place for it at -4 EBP. That corresponds to this location, our first temporary word on the stack. And we're going to just put the literal 1 there. Okay, so that creates that variable val and gives it the initial value of 1. All right. The next thing we're going to do is call shelper from sfact, and to do that we need to set up the arguments for that procedure call. Now this procedure shelper has 2 arguments, so we're going to need to push both of them onto the stack. So the first thing we need to do is, remember we pushed the arguments in reverse order, so the second argument, then the first argument. Here is the second argument, the address of val. So what we've done is used an effective address computation instruction to compute that address. Remember, just that -4 EBP. That's this location right there where we've stored val. And we're going to put that address in EAX. Okay. Then push EAX onto the stack. And that puts our first argument onto the stack. And that is an address that points back to val. Okay? The next thing to do is to push the other argument, x. Remember we had stored that in EDX, So we can just push that value of that register onto the stack. And we see that appear here. At this point, we call shelper, now that we have the arguments on the stack, and that will go and execute the code for shelper. And remember, in this case, shelper returns a void, so it does not have a return value. How do we get the result of what shelper does? Well, remember, it modified the value that was stored at this location, for which we provided the address as an argument, so that shelper could go and modify that location. So when we call shelper, the result we expect to happen is that now the value at that location of our temporary variable has been changed to x factorial, going through that series of recursive multiplies. Okay, so then our result for sfact, which remember does have to return an int value, is to go get that value, and it's going to do it again by just going to that address and moving the result to EAX and leaving it in that register when it executes its return, so that whatever called sfact can find x factorial in the register EAX, that int value that was to be returned. Okay, so let's just summarize that the IA32 procedure stack frame. The important points is there's a combination of instructions and conventions we need to use to get this to happen correctly. We have to prevent the functions from disrupting each other's correct behavior. Right? So that means not only figuring out where to return and pick up where you left off, but also making sure that they don't step on each other's toes and destroy the contents of registers that one function thought was going to stay the same. All right, so the stack turns out to be a great data structure for doing this, because when we call one procedure, we're going to return from that callee procedure before we return from the caller. So it has that nice property of growing the stack and then shrinking the stack on the returns. And recursion can be handled by all of these normal calling conventions. There's really nothing special we need to do. We can safely store values we need, local variables we need in the local stack frame and in callee saved registers. We put new arguments at the top of the stack and then call a function. The return value is returned in EAX, and we know where to go find it by convention. We know where we go find it in that register and use it.